Now we're going to find the equation of a line with vectors. This is instead of having just a point and the slope of the line and then find the equation, now we have a point, yes, that we know that is in the line, let's say line L, and we know that this line is parallel to this vector. Let's say this vector B has components A, B, and C, so it would be AI plus BJ plus CK. Now, knowing that this line L is parallel to B and this point P0 passes through this line, we're going to find the equation of this line. So first, because this line is parallel to this line, is a scalar of the vector B. So this line, let's say L, is equal to a scalar, let's say K, or let's say M times the vector B. We're going to put a point here, the same way as we did in the plane equation. Let's say this point is P, and has components X, Y, and Z. This point P naught is X naught, Y naught, Z naught. So this distance, this is P naught P, is equal to X minus X naught, comma, Y minus Y naught, comma, C minus C naught, all put times I plus times J plus and times K. Alright, so this distance is going to be a scalar of this vector. So here MV is equal to X minus X naught I plus J minus J naught, Y minus Y naught, J plus C minus C naught, okay? Usually instead of putting M, usually they use T, but I don't like to use T because it can be confused with time, so I say M. Alright, this M also could be negative, and so indicate the distance between this point and this P. Instead of here, would be in the other direction. Alright, well, so M can vary, but it's just a constant, that this is a scalar multiplied times this vector that gives us this distance between P naught and P. So this distance is equal to a scalar of this distance, and is in this line. Alright, so we have X minus X naught and Y minus Y naught. All this is equal to M divided M times B. So we have B is A, B, C. So we have M times A, Y plus B, J plus C, K is equal to X minus X naught I plus J minus J naught, Y minus Y naught J plus C minus C naught K. So because this term has I, this term is the same as M times AI. So we're going to put this side equals to this side, this equals to this, and this equals to that. So it's M A I is equal to X minus X naught I. Next is, this is one equation. The other equation is M B J is equal to Y minus Y naught times J, and the other is C minus, well, M C K is equal to C minus C naught K. Alright, so first we can eliminate the i's and Here is I with this I, this j with this j, and this k with this k, and we just left with ma equals x minus x naught, mb equals y minus y naught, and mc equals c minus c naught. So if we want to isolate the m, we can say m is equal to x minus x naught divided by a, but here m is also equals to j minus j naught divided by b, and also is equal to c minus c naught divided by c. These are called the equations of the line. These are the similar or symmetrical equations of the line. These are called the parametric equations of the line. When we solve for m, we have these three equations, and these are symmetric equations. So these are the equations of the line. This is in a parameterized way. This is again are three linear equations that represent a line in three dimensions. Here the trouble is, let's say that we have a equals 0. So here would be the a component, and the I component of this vector is 0. That means that this vector line lies in the yc plane. So would be in this parameterized equation, because a is 0, we just have 0 times n. 0 is equal to x minus x naught, and so x is equal to x naught. That means that the x of the line is always equal to x naught, so it's always equal to this point. So no matter what is y or what is z, x is always this. Let's say that x is in this direction, so x is always this point. So we have this vector now is in the yc plane. So the yc plane, let's say, would be in this plane. If I have here x in this direction, x in this direction, y in this direction, y, and c in this direction. So because the line has 0, this b has 0 component in the x direction, this means that this vector is in the gc plane, that is this plane. It is the plane in which x is perpendicular. So we are in x is perpendicular. So we are in the gc plane. In this plane is the vector b living. So here is vector b living in the gc plane. Here it is. Now we have that our line that is parallel to this line, and that has the point P, let's say, in the line, would be this line L that is perpendicular. But let's look that the x, all the x's that this line can take is just one x, and is the x that is the x coordinate of the point P, this point P. That is because the a component of this vector was 0, and we know that our line is parallel to this line, and we know the coordinates of the point P naught. So for that, this line in which the a component of this line of this vector that is parallel to this line is 0. So this line is a line that is perpendicular to the y, that lies in the yc plane. That's one thing that lies in the yc plane. So if we have b naught, b0 b is equal to 0, that is that the vector only lies in the xz plane, so it would be in this plane. That means that our vector is here. We have a line that is parallel to this, and let's say that contains the P point, or here the P point, so this would be the line L that lies in the xz plane. Alright, and that is parallel to this line.